Here we will be studying an important infinite series known as a geometric series. As you will see, it is the sum of a geometric sequence. Here's the definition. A geometric series is a series where successive terms of the sum have a common ratio, just like that of a geometric sequence. In other words, a geometric series is the form the sum as n goes from 0 to infinity of c times r to the n power, where c and r are specific constants. R is called the common ratio, and c is the first term of the sum, since when you expand this, when n is first 0, you get just c, when n is 1, you get cr, when n is 2, you get cr squared, etc. Before we dive deeply into geometric series, we need to make sure we can identify the value of c and r for a specific geometric series. So here's our first example. The sum as n goes from 1 to infinity of 1 over 2 to the n is a geometric series. What is c and what is r? First, notice that the lower bound on the series here is 1, where it is 0 up here. And also notice that we do not simply have one number r raised to the nth power. We only have the denominator of 2 raised to the nth power. We're going to have to adjust this to make it look like this. So, first, c is the first term of the sum. This particular series starts at 1, so we can simply plug in n equals 1 to find the first value of the sum, which would be the value of c. Hence, we have c is equal to 1 over 2 to the first power, which of course is 1/2. So our c value is 1/2. Now we need to know what r is. Well, again, we need to have a common ratio r raised to the nth power. Right now, we have a 2 raised to the n power, but that 2 is not the value of r. The whole expression needs to be raised to the n power. And we can do that quickly by using some of our old school exponent laws to rewrite this. So we have the sum as n goes from 1 to infinity of 1 over 2 to the n. We can rewrite this sum as the sum as n goes from 1 to infinity of 1 to the n over 2 to the n, since 1 to the n is equivalent to 1 for every finite value of n. Now, using your exponent laws, we can rewrite this as the sum as n goes from 1 to infinity of 1/2 to the n power. Now that we have a number raised to the nth power, that is our ratio r. So r is equal to 1/2. We have successfully identified c and r for this geometric series. However, there might be a scenario where you would want to write this in this exact form. So notice that a key to this form is that we need to drop this lower limit down to 0. And to do so, we'd have to just make an adjustment in the term. So if you drop that by 1, the 1/2 to the n power will need to change to 1/2 to the n plus 1. You drop the n by 1 for the lower limit, so that means you need to take the exponent up by 1 to compensate for that. And you can check to be sure this is right, because here the first value is n, 1/2 to the 1 is 1/2, whereas here you got the first value of n is 0, 1/2 to the 0 plus 1 is also 1/2. So these two series are equivalent. Now, to make this series look exactly like this, we have the lower bound is the same, but we need to have it in the form c times r to the n. Right now we have r to the n plus 1. Using our exponent laws, we can rewrite that expression, and we would get that this is equal to the sum as n goes from 0 to infinity of 1/2 to the n power times 1/2. And with it written like this, you can now see the common ratio is 1/2, since that's what's being raised to the n power, and the c value, which is the starting value of the sum, is 1/2. Now that we've found c and r for this geometric series, let's explore this geometric series a little bit further. First, we'll do that numerically. So we are going to complete the table below, and we want to see what does the series appear to converge to. Again, this notation, S sub 10, S sub 100, this is your partial sums notation. So S sub 10 means the sum of the first 10 terms, S sub 100 is the sum of the first 100 terms, and S sub 1 million, for example, is the sum of the first 1 million terms of the series. We certainly would not do a computation like this by hand. Using technologies such as Desmos, you will be able to see that when rounded to the thousandths place, S sub 10 is 0.999. Then with the rounding capabilities of the calculator I'm using, this comes out to be 1, and the rest come out to be 1. These are not exactly 1, but when rounding to the thousandths place, that's where it rounds to. So as we've discussed prior to this, numeric evidence does not constitute proof. Because, for example, this is a sum of infinitely many terms, whereas S sub 1 million is only the sum of the first 1 million terms of this series. There's still infinitely many more that would need to be added on. But as of now, it appears, because this is leveled off so quickly as we increase the size of n, that this series perhaps does in fact converge, and perhaps it converges specifically to 1. In order to determine that, we need to look at this analytically. To do this analytically, we will look step by step at some symbolic computations that will allow us to figure this out. So first, we're going to write the nth partial sum, S sub n, as a sum of the first n terms of a general geometric series of this form. So we've got S sub n is equal to, when n is 0, this is simply just C, plus when n is 1, this is simply CR, when n is 2, this is simply CR squared, dot, dot, dot. Now this is not going on forever because this is a partial sum. The last term would be CR to the n minus 1. And the reason this is n minus 1 is because we need a total of n terms, and the first value had r to the 0 in it. So hence the reason we stop here at r to the n minus 1. Now let's take this expression and write r times S sub n. So r times S sub n would simply be CR plus CR squared when you distribute the R into all those terms, plus CR cubed, plus dot, 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 CR to the n power. Now we're going to write an expression for S sub n minus R times S sub n. So we are taking this sum and subtracting this sum from it. But notice here, a whole lot of terms will cancel out. When we subtract these two, CR minus CR would be 0, CR squared minus CR squared would be 0, etc., etc. So the only thing that we have left in this difference is that first C up at the top here, and the only thing that would be left is this thing in the bottom, and it would be minus CR to the n. Now notice that S sub n minus r times S sub n is the same thing as S sub n times the quantity 1 minus r by first factoring out S sub n. And what we're going to do is now isolate S sub n by dividing both sides of this expression by 1 minus r. So we're going to divide this by 1 minus r and this by 1 minus r. Over here, which is the same thing as this, when you divide it by 1 minus r, you would only have S sub n left. And over here, we're going to divide that by 1 minus r. We get C minus C times r to the n over 1 minus r. And here we can factor out the C in the numerator and get C times the quantity 1 minus r to the nth power over 1 minus r. Lastly, we are now going to look at what conditions for r will make the sequence of the partial sums converge or diverge. Essentially, this is the same thing as saying what conditions for r will make the geometric series converge or diverge. So we need to take the limit as n approaches infinity of our S sub n term, which is C times the quantity 1 minus r to the n power, all over 1 minus r. Instead of evaluating this limit formally, we are going to approach it informally to save us a good amount of time. So first, imagine if you had r was some number between -1 and 1. For demonstration purposes, let's let r be a half, and we'll let c be 1. So we've got the limit as n approaches infinity of 1 minus 1/2 to the nth power over 1 minus 1/2. We need to see what happens to this function as n approaches infinity. And let's think about the continuous version of this and its graph. So essentially, you've got an exponential function here with an r value between 0 and 1. That means you're dealing with exponential decay. But as you multiply this thing by -1, you're going to end up having an exponential decay curve that is reflected over the x-axis and then shifted up by 1. So you get something that looks like this, where you've got a horizontal asymptote here at y equals 1. And of course, the bottom number here is a finite number. So with this being finite over finite, that means this limit would be a finite number, which would imply that the S sub n's will converge when r is between -1 and 1. This is equivalent to saying that the S sub n's will converge when the absolute value of r is less than 1. When r is outside of -1 and 1, that is specifically when the absolute value of r is greater than or equal to 1, which of course is when r is less than or equal to -1, or when r is greater than or equal to 1, we then will get divergence of our sequence. The reason is because pretend, let's say is 5 here. If this was 5, you're going to have 5 to the n is going to be exponential growth, and then of course 1 minus that thing, this thing's going to go off to -infinity. No matter what that specific numeric number is here, it won't affect that. So those limits would go off to -infinity, which means the sequence of partial sums would diverge. In summary, we have the sequence of partial sums will converge when the absolute value of r, or the absolute value of the common ratio, is less than 1. And we will have a divergent sequence of partial sums for the geometric series when the absolute value of r, or the absolute value of the common ratio, is greater than or equal to 1. We now can state our geometric series theorem, and we can then do practice with it.